So hello everyone, today our team would be presenting on hierarchical clustering with mainly focus on three important approaches: agglomerative clustering, divisive clustering and then merge. So let's understand what clustering basically is. So clustering is an important concept in machine learning due to which we can combine similar data into meaningful groups. Clustering can be used in various techniques in today's world such as image recognition, recommendation systems and various other stuffs. So let us now understand what hierarchical clustering basically is. So basically hierarchical clustering is an unsupervised machine learning technique, meaning that it groups data without using labeled examples. Unlike k-means clustering, where we must decide the number of clusters before running the algorithm, hierarchical clustering creates tree-like structures called dendrograms. These dendrograms later allow us to decide how many clusters do we actually want by cutting the tree at various levels. It has various different advantages such as easy visualization and flexibility as well, and various other stuffs. So now that I have given the concept and overview of hierarchical clustering, let us actually understand how hierarchical clustering basically works. Thank you.
On to the next slide, overview and concepts. Hierarchical clustering organizes data into a structure called a dendrogram, which represents how clusters are merged or divided over time. The final clustering result depends mainly on two factors: the distance measured between 2 points, the linkage method used to combine clusters. Different linkage methods produce different cluster shapes and structures. One important consideration is the trade-off between interpretability and scalability. While hierarchical clustering is easy to understand and visualize, it becomes computationally expensive as the dataset grows larger. Now let's explore the first hierarchical clustering technique. Moving on to the next slide, agglomerative clustering. Agglomerative clustering follows a bottom-up approach. Initially, every data point is treated as its own cluster. The algorithm repeatedly merges the two closest clusters until all points belong to one large cluster. Several linkage methods determine how clusters are merged, including single linkage, complete linkage, average linkage, word linkage. Although agglomerative clustering produces highly interpretable results, it requires significant computation and memory when working with very large datasets. Next, we will look at the opposite approach.
Coming to the next one, which is divisive clustering. So, divisive clustering follows a top-down approach, which is instead of beginning with many individual clusters, it starts with all data points grouped into as one large cluster. The algorithm, which repeatedly divides this large cluster into smaller clusters until a stopping condition is reached. Compared to the agglomerative clustering, divisive clustering is like generally more computationally intensive because it determines the best split at every step, which is challenging. It is mainly used when understanding large-scale cluster structures, which is more important than all the computational efficiency. So now let's move to the hierarchical clustering algorithm specifically designed for large data sets. So coming to the next part, which is BERT fundamentals. BERT stands for balanced iterative reducing and clustering using hierarchies. It is designed to such as to which efficiently process very large data sets instead of storing every individual data point, but stores compact summarizes called clustering features, which significantly reduces more memory usage and enables near linear execution time, making BERT much faster than like all these traditional hierarchical clustering methods. Which is the use of clustering features also allows BERT to perform incremental clustering. So now clustering features are organized. So
Coming on to CF trees and parameters. So the clustering features are stored in a special data structure known as the CF tree. The CF tree is a high balance tree that stores summarized cluster information rather than storing the raw data. Its performance depends on three important parameters. The first is branching factor, the second is leaf factor, and the third is threshold. Among these three features, the threshold controls the maximum cluster radius and has the greatest impact on cluster compactness and memory usage. Carefully, carefully, if you look at the parameters, you can see it helps balancing clustering accuracy and computational efficiency. Now, coming on to the next thing, phases and comparison. So, phases and comparison. So, here in phases and comparison, the Beach algorithm operates in four phases. The first is building the CF tree, the second is optionally condensing the tree, the third is performing global clustering on the summarized data, and the fourth is optionally refining the final clusters. So, So coming into this, comparing the agglomerative and divisive clustering, BEAST offers much better scalability and lower memory consumption. Although it may sacrifice a small amount of clustering precision, it provides a significant improvement in speed and efficiency when handling large datasets. So coming into the last part, that is conclusion. So here you can conclude that hierarchical clustering creates a tree-like representation of data called dendrograms, whereas agglomerative clustering builds clusters by merging smaller groups from the bottom up. Here you can see that divisive clustering works in the opposite direction by repeatedly splitting larger clusters for but the problem arises when there is a very large amount of datasets. So for very large datasets, BIDS is the preferred approach because it provides faster execution, efficient memory usage, and scalable performances. So looking at all those techniques, we can conclude that every technique has its own strengths and the appropriate choice depends on the size of the datasets and the specific parameters. Yeah. So thank you.